At the edge of the known universe, scientists have found something that shouldn't exist. A black hole so enormous, it defies every law of cosmic growth we understand. Its mass is billions of times greater than our Sun, but it shouldn't be possible. According to physics, such a thing couldn't have formed in the age of the universe we live in. And yet, it's there, silent, consuming, rewriting the story of how everything began. The discovery came quietly, as most revolutionary findings do. No grand announcement at first, just astronomers sifting through data from telescopes pointed at a patch of sky so distant, the light reaching us began its journey when the universe was barely a child. They were hunting for quasars, those brilliant beacons powered by black holes feeding on matter with such violence that they outshine entire galaxies. But what they found wasn't just another quasar. It was an impossibility made real. The object goes by the catalog designation JZOL5294351, though that sterile name does nothing to capture what it represents. When the measurements came back, when the calculations were checked and rechecked, the team realized they were looking at a supermassive black hole with a mass exceeding 17 billion times that of our Sun. Perhaps more. The uncertainty isn't ignorance. It's the sheer difficulty of weighing something so distant, so massive, that our usual cosmic yardsticks begin to bend under the strain. But mass alone doesn't tell the full story. What makes this discovery genuinely disturbing to cosmologists is when this black hole existed. The light we're seeing left that region of space over 13 billion years ago, less than a billion years after the Big Bang itself. In cosmic terms, that's infancy. The universe was still cooling, still forming its first stable structures, still figuring out how to make stars in any meaningful quantity. And there, in that young darkness, sat a black hole more massive than some we see in the mature universe today. To understand why this creates such profound confusion, you need to understand how black holes are supposed to grow. And that story begins not with the monsters, but with the deaths of ordinary stars. Black holes don't appear from nothing. They're born from collapse. The catastrophic implosion of matter into a point of such density that space itself tears around it. For most of cosmic history, this happens when massive stars exhaust their nuclear fuel. The outward pressure from fusion that held them up for millions of years suddenly vanishes. Gravity, patient and relentless, wins. The core collapses in fractions of a second. If the star is large enough, nothing can stop this collapse. Not neutron pressure, not quantum mechanics. The core becomes a singularity, wrapped in an event horizon from which not even light escapes. These stellar mass black holes clock in at anywhere from about 5 to perhaps 100 times the mass of the Sun. They're the common ones, scattered throughout galaxies like ours, the remnants of generations of dead stars. We've detected them through gravitational waves when they collide, through the X-rays they emit as they feed, through the distortions they create in space-time itself. But the black holes at the centers of galaxies, the supermassive ones, are different beasts entirely. They don't form from single stars. They can't. No star is massive enough to directly create something a billion times heavier than the Sun. Instead, supermassive black holes grow. They accumulate mass over time, pulling in gas and dust and occasionally entire stars that wander too close. This process is called accretion, and it's governed by physics that, while violent, follows predictable rules. Here's where the problem begins. Accretion isn't fast. When matter falls toward a black hole, it doesn't plunge straight in. It forms a disk, spiraling inward, heating up from friction until it glows brilliantly. This is how we spot many black holes, not by seeing them directly, but by watching the inferno of matter swirling into oblivion. But there's a limit to how quickly this can happen, a ceiling built into the laws of physics that can't easily be broken. The limit is called the Eddington luminosity, and it arises from a balance between gravity and radiation. As matter accelerates toward the black hole and heats up, it emits radiation, light, X-rays, all across the spectrum. This radiation pushes back on the infalling matter. Push too hard, and you blow the material away before it can be consumed. The black hole creates its own shield, a kind of cosmic traffic jam that prevents it from eating too quickly. Given this limit, we can calculate how fast a black hole should be able to grow. Start with a seed, say, a black hole 100 times the mass of the Sun, formed from one of the universe's first stars. Let it feed continuously at the maximum rate allowed by physics. Let it gorge itself on every scrap of available matter for 1 billion years. It still won't reach 17 billion solar masses. It won't even come close. This is the heart of the paradox. The black hole, J0529-4351, and others like it discovered in the early universe, grew too large, too fast. They violated the cosmic speed limit for growth. And when something in nature breaks the rules this fundamentally, it means one of two things. Either we've misunderstood something critical about how these objects form, or the universe had mechanisms in play during its youth that we've never witnessed. Let's consider what we thought we knew. The standard model of supermassive black hole formation goes something like this. In the early universe, the first stars formed from clouds of pristine hydrogen and helium. These population 3 stars, as astronomers call them, were likely much more massive than modern stars, perhaps hundreds of times the mass of the Sun. They lived fast and died young, some collapsing, into the first black holes within a few million years of the Big Bang. These seed black holes would have sat at the centers of proto-galaxies, pulling in matter from their surroundings. Slowly, over hundreds of millions of years, they would grow. Galaxies would merge, and their central black holes would spiral toward each other, eventually coalescing into larger black holes. More gas would fall in. More stars would be devoured. Gradually, incrementally, the monsters we see today would form. This model works beautifully for the black holes we observe in the relatively nearby universe. Sagittarius AB, the 4 million solar mass black hole at the center of our own Milky Way, fits this picture perfectly. So do the billion solar mass giants we've found in galaxies a few billion light years away. They had time. The universe gave them 10, 12, 13 billion years to grow to their current sizes. But J0529-4351 didn't have that time. It existed when the universe was barely 700 million years old. It reached a mass that should have taken many billions of years to accumulate in a fraction of that time. When the first of these ultra-distant, ultra-massive black holes was discovered in 2011, astronomers assumed it was an outlier, a statistical fluke. Perhaps the measurements were wrong, or the redshift calculation was off, or some unusual circumstance allowed this one object to grow faster than normal. But then they found another, and another, and another. Each new detection tightened the noose around conventional theory. These weren't flukes. They were a population. Early supermassive black holes appeared to be common, scattered throughout the infant universe in numbers that made no sense. Some of them were even more massive than J0529-4351, pushing past 20 billion solar masses, existing at times when the universe was barely 500 million years old. The James Webb Space Telescope, launched in late 2021, made the situation worse. Its infrared eyes are specifically designed to peer at the earliest epochs of cosmic history, to see the first galaxies forming in the darkness. And what it found were more massive black holes, even earlier, even more problematic. The discoveries kept coming, each one another nail in the coffin of our comfortable models. Cosmologists were forced to confront an uncomfortable truth. Something fundamental was missing from our understanding of the early universe. The hunt for answers has led theorists down several paths. each more speculative than the last. The first question they asked was simple. What if the seeds were bigger? In the standard picture, black holes start from stellar collapse, giving you seeds of maybe 10 to 100 solar masses. That's not much to work with. But what if, in the early universe, conditions allowed for the formation of much larger seeds right from the start? What if you could bypass the stellar phase entirely and create black holes of 10,000, 100,000, or even 1,000,000 solar masses within the first 100 million years after the Big Bang? This idea is called direct collapse. Instead of waiting for stars to form and die, you'd need a cloud of gas massive enough and dense enough to collapse directly into a black hole without ever igniting fusion. The problem is, this doesn't happen easily. Gas clouds want to fragment. As they collapse, they form clumps that become individual stars. Getting a smooth, coherent collapse into a single massive object requires very specific conditions. One possibility involves pristine gas clouds, regions that somehow avoided being enriched by metals from earlier stellar generations. Without heavier elements, the gas can't cool efficiently. Cooling is what allows clouds to fragment into smaller pieces. Keep the gas hot, and it might collapse as one unified mass, creating what's called a direct collapse black hole. Another scenario involves the collision of proto-galaxies in the early universe. When two gas-rich galaxies merge, they can funnel enormous quantities of matter toward their centers. If this happens violently enough, quickly enough, you might compress enough gas to trigger direct collapse without stars ever forming. Computer simulations have shown this is at least theoretically possible, though the conditions required are extreme. But even if you grant these scenarios, even if you allow for seeds of 1,000,000 solar masses appearing in the first 100 million years, you still face the Eddington limit. You still have the problem of growth rate. Getting from 1,000,000 to 17 billion in 700 million years requires sustained feeding at or above the maximum theoretical rate, with no interruptions, no breaks, no periods where the black hole goes hungry. That's asking a lot of the universe. Some physicists have suggested that maybe the Eddington limit isn't as strict as we think. It's based on assumptions about how matter behaves as it falls toward a black hole. Assumptions that might not hold in the chaotic, dense environments of the early universe. Perhaps there were periods of super-Eddington accretion, where black holes temporarily exceeded their theoretical feeding limits. We've actually observed hints of this in some modern quasars. During outbursts or particularly active phases, black holes can consume matter faster than Eddington physics would predict. But these episodes are brief, lasting thousands of years at most. To explain the early monsters, you'd need super-Eddington feeding sustained for hundreds of millions of years. You'd need the universe's most violent feeding frenzy, happening continuously, without pause. It's not impossible, just deeply unlikely. Another idea ventures even further into speculative territory. What if these aren't the remnants of stars at all? What if they're primordial black holes, formed in the immediate aftermath of the Big Bang itself? In the first fractions of a second after the universe began, quantum fluctuations could have created regions of higher density. If these fluctuations were large enough, they might have collapsed directly into black holes before the universe had time to smooth itself out. These primordial black holes would have existed before the first stars, before the first atoms even formed. They could have any mass, depending on the size of the initial fluctuation, including masses large enough to seed supermassive black holes. The problem with primordial black holes is that we have no direct evidence they exist. They're a theoretical possibility, allowed by physics but never confirmed. And if they were common in the early universe, we should see other signatures of their presence: gravitational effects on the cosmic microwave background, statistical patterns in the distribution of matter that we haven't clearly detected. Yet the idea persists because it elegantly solves the timing problem. If supermassive black holes don't need to grow from small seeds, if they started large right from the beginning, then the Eddington limit becomes less of a barrier. You'd still need rapid growth, but not impossibly rapid growth. There's another angle to this mystery that doesn't get discussed as much, but it's equally troubling. It's not just about the black holes themselves, it's about the galaxies they sit inside. Supermassive black holes don't exist in isolation. They're always found at the centers of galaxies, and there's a relationship, almost a partnership, between a galaxy and its central black hole. The black hole's mass tends to correlate with the mass of the galaxy's central bulge, the dense spheroid of stars surrounding it. This relationship is tight, predictable, and holds across nearly every galaxy we've observed. The correlation suggests that black holes and galaxies grow together, influencing each other through feedback mechanisms. When a black hole feeds aggressively, it launches powerful jets and winds that heat up surrounding gas, preventing it from collapsing to form new stars. This regulates the galaxy's growth. Conversely, the galaxy provides the black hole with fuel, gas that spirals inward, keeping the monster fed. But J0529-4351 and its siblings throw this relationship into question. These black holes are so massive, so early, that their host galaxies shouldn't have had time to build up the stellar populations we'd expect. Either the black holes grew much faster than their galaxies, breaking the correlation we see everywhere else, or the galaxies themselves formed far more rapidly than our models predict. Early observations from the James Webb Space Telescope have shown something strange. Many of these early galaxies appear surprisingly mature. They have structures, stellar populations, and chemical abundances that suggest longer formation times than should be possible. It's as if the early universe was running on fast forward, compressing billions of years of evolution into just a few hundred million. This has led some astronomers to wonder if our understanding of the early universe itself is flawed. Maybe conditions in those first epochs were radically different than we imagine. Maybe gas was denser, star formation more efficient, or the clustering of matter more extreme. Maybe the universe's youth was not a time of slow awakening, but of explosive, chaotic growth that we've only begun to appreciate. There's a philosophical dimension to all of this that's worth sitting with. Every time we point our telescopes deeper into space, we're looking further back in time. The light from J0529-4351 has been traveling toward us for over 13 billion years. We're not seeing the black hole as it is now. We're seeing it as it was in the ancient past, in the universe's childhood. And what we're seeing is that the universe was stranger, more complex, more precocious than we thought. We expected to look back and find simplicity, a young cosmos still figuring itself out, dominated by small structures and modest objects. Instead, we're finding giants. We're finding maturity and complexity appearing far earlier than they should. It's humbling, in the best sense of the word. Every generation of astronomers believes they've figured out the broad strokes of cosmic history, only to have new observations reveal deeper layers of mystery. The ancient philosophers wondered if the universe had a beginning at all. A century ago, we proved it did, but thought it might be static, unchanging. Then we discovered expansion, the Big Bang, the cosmic microwave background. With each answer came new questions. The discovery of impossibly massive early black holes is the latest chapter in this story. It tells us that even our most sophisticated models, built on decades of observation and theory, are incomplete. There are mechanisms at work in the universe that we haven't witnessed, processes that only occurred in those first cosmic moments, perhaps never to be repeated. Or perhaps they're still occurring, in regions too distant or too dark for us to see yet. One of the more intriguing proposals to emerge recently involves the nature of dark matter itself. We know that roughly 85% of the matter in the universe is dark, invisible to our telescopes, interacting with normal matter only through gravity. We don't know what it is. We've never directly detected a dark matter particle. We infer its existence from the way galaxies rotate, the way light bends around galaxy clusters, the way structure formed in the early universe. But what if dark matter played a more direct role in forming the first supermassive black holes? Some models suggest that dark matter could have clustered more tightly in the early universe, forming dense halos that acted as gravitational wells, pulling in normal matter. These halos might have been the scaffolding on which the first structures formed. If dark matter concentrated strongly enough in certain regions, it might have enabled the rapid collapse of massive gas clouds, creating either large seed black holes or the conditions for extremely efficient feeding. There are even more exotic ideas. Some physicists have speculated about dark matter particles that could directly collapse into black holes under the right conditions, or about interactions between dark matter and normal matter that we don't yet understand. These are fringe theories, not widely accepted, but they illustrate how far scientists are willing to push the boundaries when faced with a genuine mystery. The truth is, we don't know. And that's not a failure of science. It's a feature. It's the engine that drives discovery forward. Let's zoom out for a moment and consider the broader implications. If supermassive black holes formed earlier and grew faster than we thought possible, what does that mean for the history of galaxies, for the formation of stars, for the emergence of the large-scale structure we see in the universe today? Black holes aren't just passive objects. They're among the most energetic phenomena in the cosmos. When they feed, they release tremendous amounts of energy, often outshining the combined light of every star in their host galaxy. This energy doesn't just disappear. It heats gas, drives winds, triggers shock waves. It can either enhance star formation by compressing gas clouds or suppress it by blowing gas away entirely. In the modern universe, this feedback is crucial for explaining why galaxies look the way they do. Without it, computer simulations produce galaxies that are too dense, too gas-rich, too blue with young stars. The black hole feedback is the thermostat, regulating how efficiently gas turns into stars. But if massive black holes existed very early, they would have started influencing their environments far sooner than we expected. They would have injected energy into the intergalactic medium while it was still hot and diffuse, potentially affecting how the first large galaxies formed. They might have altered the reionization process, the epoch when the first stars and quasars produced enough ultraviolet light to strip electrons from neutral hydrogen atoms, making the universe transparent again. Some researchers believe that early supermassive black holes might be the missing ingredient that explains why the universe reionized as quickly as it appears to have. The timing matches up. Reionization seems to have happened between 400 million and 700 million years after the Big Bang, right when these massive black holes were already up and running. But this creates a chicken and egg problem. If black holes helped reionize the universe, and reionization changed the conditions for gas accretion and star formation, then the black holes were influencing the very environment that determined their own growth. The feedback loops become tangled, interdependent, difficult to model. It's like trying to understand a forest by studying one tree. Everything connects to everything else. The most unsettling possibility is one that scientists don't often say out loud, but it lurks in the background of every conversation about these objects. What if our models of black hole formation aren't wrong, but our understanding of time itself in the early universe is incomplete? Einstein's general relativity tells us that time is not absolute. It flows at different rates depending on gravity and motion. Near a black hole, time slows down dramatically. To an outside observer, an object falling toward an event horizon appears to freeze, asymptotically approaching the boundary, but never quite reaching it. The early universe was a very different place. Space itself was expanding rapidly, carrying matter apart. The density was higher, the temperature was higher, and the gravitational fields were more intense. Some cosmologists have wondered if the relationship between cosmic time, the time measured by the expansion of the universe, and the local time experienced by matter in dense regions might have been different than we assume. Could matter near forming black holes have experienced more local time than the cosmic clock would suggest? Could the processes of collapse and accretion have run faster, from the perspective of the infalling matter, than our calculations indicate? This is highly speculative. There's no direct evidence for it, but it illustrates how deeply these discoveries have shaken our confidence. When faced with something that shouldn't exist, scientists will question everything, even time itself. Geofroid 29 to 4351 continues to be studied. More observations are planned, using every major telescope available. Astronomers want to measure its mass more precisely, to study the spectrum of light from its accretion disk, to understand its host galaxy better. Each new piece of data might provide a clue. Meanwhile, the search continues for even earlier, even more massive black holes. If the trend holds, if we keep finding giants in the universe's infancy, the theoretical crisis will deepen. At some point, the weight of evidence will force a paradigm shift, a fundamental rethinking of how structure formed in the cosmos. That shift might come from a breakthrough in dark matter physics. It might come from new models of gas dynamics in the early universe. It might come from a discovery we haven't even imagined yet, spotted in data from some future telescope that can see further, clearer than anything we have now. Or it might come from a realization that we've been asking the wrong questions all along. There's a particular kind of vertigo that comes from contemplating objects, like JASR 529-4351. It's not just their size, though 17 billion solar masses is genuinely difficult to wrap your mind around. It's not just their age, though existing less than 1 billion years after the Big Bang is profoundly ancient. It's the realization that they're windows into epochs we can barely understand. When that black hole formed, the universe looked nothing like it does today. There were no planets, no complex chemistry, no life anywhere as far as we know. Just hydrogen, helium, and the first fragile structures pulling themselves together from the cooling plasma of creation. And in that primordial darkness, somehow, impossibly, monsters were born. We often think of scientific progress as a steady accumulation of knowledge, each generation building on the last, filling in the map of reality piece by piece until the picture is complete. But the history of science tells a different story. It's full of moments like this, discoveries that don't fit, observations that contradict the established view, phenomena that shouldn't exist but do. These aren't setbacks, they're invitations. They're the universe tapping us on the shoulder, reminding us that reality is always stranger, always deeper, always more interesting than our current models can capture. The late physicist John Wheeler once said that we live on an island of knowledge, surrounded by a sea of ignorance. As the island grows, so does the shoreline, our contact with what we don't know. Every answer reveals new questions. Every solved mystery points toward deeper mysteries waiting beyond. JO 529-4351 is one of those deeper mysteries. It sits at the intersection of our most profound questions about time, matter, gravity, and the origin of structure in the cosmos. Understanding it will require new ideas, new observations, possibly new physics. But that's what makes it beautiful. That's what makes it worth studying. Not because it fits neatly into our equations, but because it doesn't. Not because it confirms what we thought we knew, but because it challenges us to think harder, look deeper, imagine more boldly. Somewhere in the data, in the observations we haven't made yet, or the theoretical insights we haven't had, there's an answer waiting. Maybe several answers, maybe a whole new framework for understanding how the universe put itself together. Until then, J0529-4351 remains what it's been since the first light of its accretion disk began its 13 billion-year journey to our telescopes, a question mark written in the fabric of space-time. A reminder that the cosmos is not required to make sense to us. It simply is, in all its impossible, magnificent strangeness. And here's what makes nights darker and stars brighter, if you let yourself feel it. J0529-4351 is not alone. It's not the only impossible black hole in the early universe. It's one of many. The James Webb Space Telescope keeps finding more. Each new survey, each deeper observation, reveals more giants that shouldn't be there, more questions that don't have answers yet. Which means the mystery is bigger than one object. It's systemic. It's telling us something fundamental about how the universe works, something we've missed despite centuries of looking. Maybe the early universe was a wilder, more violent place than we imagined. Maybe the first billion years were a cosmic forge, running hot and fast, creating structures in ways that never happened again. Maybe the rules were different when everything was young, when gravity was pulling the first matter together, when dark matter halos were collapsing, when space itself was still ringing with the echoes of its own explosive birth. Or maybe, and this is the thought that keeps cosmologists awake at night, maybe the rules weren't different at all. Maybe we just don't understand them as well as we think we do. There's a human tendency to want closure, to want the mystery solved, the equation balanced, the answer revealed. But the greatest discoveries often come from sitting with the uncertainty, from learning to be comfortable not knowing. J0529-4351 invites us to do that, to look up at the night sky and remember that behind the gentle twinkling of stars lies a universe of extremes, of black holes billions of times more massive than our sun, of galaxies colliding in slow motion, of space itself expanding and carrying everything apart. And buried in that vastness, hidden in the light from the most distant reaches we can see, are clues to mysteries we haven't solved yet. Puzzles that our best minds are still working on. Questions that might take decades or centuries to answer, if we can answer them at all. But that's all right. That's the adventure. That's what keeps science alive. The perpetual frontier, the endless horizon, the universe revealing itself layer by layer, never quite getting to the bottom because there's always another layer waiting below. J0529-4351 is too massive. It shouldn't exist, but it does. And that simple fact, that reality refuses to fit our models, is perhaps the most important lesson the universe has to teach. We are pattern-seeking creatures living in a cosmos far stranger than patterns alone can capture. And every time we think we've figured it out, the universe shows us something new, something impossible, something beautiful. If mysteries like these fascinate you, stay curious. The universe isn't done surprising us yet. It never will be.